So anytime you have a gradient in potential energy, you will have a force. So for example, if you have this flat surface like this, completely horizontal, and if I put a marble on here, there's no force on the marble. Why? Because all directions are equivalent. Why would it have a preference to go one way or another? Now, if there's a slope to this, the potential energy is changing with location because it's mgh. It depends on the height. So look at what happens. Not surprisingly, the marble basically rolls down. So anytime you have a gradient in the potential energy, you will have a force. So let's now look at these contour maps. So this is a 3D profile of a hill, and this is a flat contour map. So this is basically taking a section of it, and then you have different colors and these different contour lines that demarcate the different heights that you have over here. The topmost portion here is 250 meters, and then this is a 0 over here, basically sea level, so to speak. And the contour map indicates the same thing by location. So most maps will basically show something like this, a contour map. Now notice that this northeast slope over here is steeper than the rest of this hill. There's like a faster, more sudden drop. So accordingly, if you look at the profile of the contours over here, they are closer together. So that's indicative that the height is dropping more quickly. So you basically have a shorter horizontal run for a certain vertical height. And the slope is basically the rise over the run. So the same thing happens in the electric case. If you have a sharp needle like this that's charged to 500 volts, it's positive, you have all these positive charges on here, then as you go away from it, the electric potential drops. So there's voltage, there's potential in the air. Remember, potential is a field basically. So this drops as you go away. So it drops from 500 to 400, 300 to 200 over here. So this is very similar to that hill. How it is dropping in height, you're dropping in potential. And look, near the sharp point, the contours are close together. So it shows that for a certain distance away, a radial distance away, the potential drops faster. So that's like this a higher slope that you had in this or this hill over here. If you remember, this was a steeper slope, and correspondingly the contours are closer together. So here the same thing is happening. Where the contours are close together, the potential is dropping more rapidly, and you will end up with a stronger force on a charge. So if you were to place a charge over here, you'll feel a greater force than putting a charge over here, because the slope is greater. The potential energy changes more quickly with the distance. So this connection between the potential energy, the force, and the electric field, let's now treat this more quantitatively. So let's begin by putting a test charge Q over here. So this charge is going to get, it's a positive charge, it's going to be repelled by all these positive charges here, it's going to get pushed away. So in other words, there's an electric field that's pushing this charge away. We want to find out the relationship between the electric field and these different potential contours that you have over here. So let's see what work it takes to push this positive charge from this pink contour to the green contour, going from 200 volts to 300 volts. So, and that represents the change in the potential energy. So the work needed to move something like from this height to that height, that work is mgh. That's the increase in the potential energy. So same thing over here. So the increase in the potential energy as defined by potential, delta U is Q delta V. This is the definition of electric potential, is the potential energy per unit charge. So therefore the change in U is Q times delta V. Next, as I just mentioned, that increase in potential energy, that comes from the work needed by the hand pushing this charge over there. So the work needed, the external work, that's equal to the force from a hand, for example, times the delta R, just the definition of work that you have over here. On the other hand, the force that you're pushing against is the electric force. So that force, it's in the opposite direction, but the magnitude of that force is E times Q, electric field times the charge. That's the definition of electric field. The force felt by a charge is the electric field times the charge. So hence EQ, and you have the delta R carried over from here. So now you have a long string equation with many things going on. Let's make a connection between the second thing over here and this last thing over here. So the things inside this green dashed green line that you have over here. So that then brings us to this connection. Q delta V is equal to minus EQ delta R. So what you have right over here. So now in this case, you can cancel the Q's because it's common, and this represents E in terms of the gradient of the potential. So E equals negative gradient of the potential minus delta V over delta R. That's the negative of the gradient. So, and this agrees with our intuition, like if you have no slope, there's no net gravitational force on this thing, it's cancelled by the normal force. So the object won't, like the marble won't roll around. And then if you have a slope, you have a gradient in the potential, the gradient in the height. So as a result, there's going to be a net gravitational force, which will cause the thing to roll downwards, basically. The negative sign reflects the fact that the force is in the opposite direction of the gradient. If you pour water on a hill, it flows down, but the slope is upward. So hence the negative sign. So similar to what you have in the case of gravity. And for those of you who are into calculus and so on, here's the optional sort of more advanced version of this. The electric field is negative of the gradient of the potential. So this gives you a full vector connection between the local electric field and how V is distributed spatially in three-dimensional space. So around a positive charge Q, this is a spherical charge over here. The electric field around this, the electric potential contours look like this. So the purple thing over here, that's at 500 volts. As you move away from the charge, go into space some distance away, the potential has dropped. It's like the height that's dropping. It went from 500 to 400. You go farther away, you're down to 300. Even farther, you're at 200. So the spacing between, they're concentric around the sphere, but the spacing increases as you go away. The figure is not very accurate, so it may not seem this way, but initially they're closer, and the potential contours get spaced farther away for every 100 volt drop. And then the electric field, that's basically shooting out like this. So notice that where the potentials are dropping more quickly, you have a stronger electric field. The field lines are more concentrated. As you go farther away, the lines get spread apart. So the electric field is more dilute. The value is dropping, and that's consistent with the fact that every drop in 100 volts takes a longer distance before you have that same drop. So here's another example of contours, electric equipotential contours, and the electric field lines around a charge configuration. So in this case, it's an electric dipole. So here you have a negative and a positive charge over here. From the positive charge, electric field lines are going outward. With a negative charge, they're going inward. It's sort of like a vacuum over here. And they go from positive to negative in between. And corresponding to that are these equipotential contours. So they don't label them as I had previously, 500 volts, 400 volts, and so on. But as you get close to each charge, it's either positive or negative, higher voltage. And as you go away, the contours represent lower and lower voltage. So basically, the potential is dropping as you go farther away. And as a result, the electric field is either away from the positive charge, or it's toward the positive charge, towards the negative charge, basically over here. And as you can see, as the contours are separating over longer and longer distances, correspondingly, the electric field lines are spreading apart. So the electric field is getting weaker. And corresponding to this dipole contour map with those field lines, here's the 3D profile of the same thing. So in the case of this is shown backward, by the way. This is positive. So the potential increases as you get closer to the charge. So that's like a greater height. With a negative charge, as I mentioned, it's like a vacuum. So as you get close to that, the electric field is inward. It's going to draw positive charges towards it, basically. So they fall into the well. And so here's a kind of another example of equipotential contours and electric field lines. And this concludes this little chapter on electric potential and potential energy.